Okay, so queuing theory is a little bit more details in engineering, marketing, service, and other business sectors. But so we just have basic concepts, and we just need to understand the concept of theory and the models, a couple of models. So let me share a PowerPoint slide. Okay, now you see my PowerPoint slides. Do you see my PowerPoint slides?
Yes, I do.
Thank you. So this is very practical, very applicable to your life and our business. So we experience every day. So it's just terminology queue, but that is the waiting line, and any service sectors. Oops. So I was explaining while we're driving on the highways, you experience the traffic congestion, heavy traffic. So to avoid any kind of congestions, you may pay extra fee to get HOV lanes and go through a faster lane through toll booths or tunnels and bridges. So when you estimate travel demand on highways, on the roads, and we also consider value of time of drivers. So some drivers will have a very high value of time, and some drivers will not have. So depend on value of time, you may pay extra money to make a shorter trip. So like this slide says, Americans spend a total of 37 billion hours a year waiting in lines. So all different types of lines can be vehicles, at retailers, wholesalers, hair salons, bank, or bridge, amusement park. And there's so many different types of servers and service stations. And if you see those service stations, customers are waiting in the line to receive service. And you also can name as so many other types of waiting lines. So waiting lines do not always contain people, but sometimes it can be music to be downloaded from cloud servers, and sub-assemble this in a manufacturing plant. So product is waiting in a process. So you see a work-in process product, electric messages on the internet. Sometimes if you try to send email to someone else, it goes to draft, right? And to be waiting to be sent by you, right? And also because of slow internet service, the email service is getting delayed. So you may see many different types of businesses, processes, with lines, waiting lines, which is a queue. So you set up the lines, and then you set up the process, and the line is being built between two actual activities. So queuing theories actually deals with analysis and management of waiting lines, because we see the waiting lines everywhere. We need to manage those lines very well. But if you go to the main campus in Jersey City, you try to talk to someone who can help you admission or register, financial aids, but some other students are waiting before you, and you never know how long it will take, how long you need to wait, right? So that's, depend on types of service, types of lines, and types of queue systems. You may have different experience of lines. So what are the purpose of queuing models? So queuing models are being used to describe the behavior of queuing systems. As I mentioned, why we're managing the queues, because we want to make the system efficient and effectively. And they also need to determine the level of service to provide. For example, if you open a restaurant or cafe, and you may need to think of, okay, how many tables you want install, or you really don't need a table because customers just coming in and take whatever they want, and or they need a table to sit down and talk with friends over coffee. So you may need to think of these kind of things everywhere for your business. Then also queuing models are used to evaluate alternate configuration for providing service. So how many ATMs should be installed to serve bank customers? And how many tellers you need to hire to serve customers? And that's not the all one. So how many computers need to be in the computer cluster at NJCU campus? So if you have many more, so you may serve customers better, but the cost will be higher, right? And if you have just few servers and people to serve students and the classes, and customers were not going to be satisfied. So between satisfaction and cost, you need to find the right optimal point, or which is optimal cost, optimal service with the minimum cost. You need to find it. So that's why we're learning queuing systems to understand. And so we have different types of queue systems. If I draw the diagram, okay. Okay, let's say we're going to the Dunkin' Donuts to get a lunch, and so it's a Dunkin' Donuts, and you arrive at the Dunkin' Donuts. Then you see the queue after class, but after the class starts, you don't see any other students, no customers in the line, so you may not see anyone, or you may see the customers. Customers are waiting. I don't know how many customers will be there, but once start to receiving service, then customer will solve it. After getting service, they're going to leave. Arrive. Depart. Or leave. Sometimes you may see both and that. So this is a waiting line. And this is service part. So I have two elements. There are whole things with call it system. Okay. So now thing is when you arrive, for example, if you drive into parking lot, if there is no slots available for you, you need to just leave, right? Then back. You cannot be in the queue, right? Because it's already, the system is full. So you may leave or blocked or leave, right? Or you're gonna be in the queue. So there are two situations, right? You're gonna be in the queue, or you may not be in the queue because you are blocked, or you need to leave because the capacity is full. Thing is, so depending on systems, you may think of multiple lanes. Right? So, and then you also have multiple servers. You may see single queue or multiple queues, or single server or multiple servers. So you may see different types of queue configurations. So let's call this as waiting time. Waiting time in a queue. This is a service time. So waiting time plus service queue is total time in the system. Total time in the system. So in a given time, how many customers are arriving in the queue? So we'll have new terminology. Lambda. Lambda is arriving rate. How many units will arrive in the queue in a given time? So again, arrival rate is the units arriving in the queue to receive service. So we call it lambda. This arrival rate follows randomness, then it'll be Poisson distribution. So if this is random variable, call it Poisson random variable. So that way, have a longer tail to the right. This is a Poisson distribution, but time, the number of units arriving in the system within a given time. We have time interval. So this follows Poisson distribution. This is now, for example, if you call customer center of your Bank of America, right? So they'll count how many calls arrive at the customer center. Then if 5 calls per hour for each server, so lambda is 5. So 5 calls per hour, that is a lambda, which follows Poisson distribution. And then I'm going to open Excel later to explain this. And then this is U, so this next term is known you to get the service. So how long it will take to get the service? If you go to the dental office to see a doctor, it take maybe 20, 30 minutes. And usually they have a 30 minutes reservation. But if it is a longer activity, it might be 1 hour. But not always will be the same service time. But it also follows random distribution. So this is the service time. Okay, this is a waiting time. This is arrival rate. Service time is the amount of time a customer spends receiving service. So this is a separate element of the service from the waiting time. So let's say this is mu. This service time follows exponential random variable. So like that. Okay. So that exponential random variable, as you see the equation on the slides. So the time interval will be between T1 and T2. Right? So they can be interval, right, or cumulative density function. So mu is the service rate. And service time is actually 1 over mu. So service rate means how many units will be served within a given time. So I'm sorry, I was making a little bit confused with the service time and service rate, but the mu is the service rate. Service time is 1 over mu. Average service time is 1 over mu. And then arrival rate is lambda. So inter-arrival time is 1 over average inter-arrival time is 1 over lambda. Okay. So now let's just see. We'll come back to this. So if arrival rate follows Poisson distribution with mean lambda, inter-arrival time follows 1 over lambda. So inter-arrival time inter-arrival times one customer arrived, and then what is how long it will take to get the next customer in the queue. So how long it will take to get the next customer in the queue. So this also follows randomness because arrival rate is random. And this customer doesn't affect the next customer's arrival time, right, or their behaviors. So those units arrival behavior are separate. So we call it memory list. Memory list property. Right? So there are examples regarding arrival rate and inter-arrival time, 1 over mu. The assumed calls arrive according to a Poisson distribution. You just assume the call arrival follows randomness, which is a Poisson distribution with the mean lambda 5 calls per hour. 5 calls per hour. Then inter-arrival times between calls average time between calls will be 1/5 hour, 0.2 hour. That means 12 minutes. Every 12 minutes, you may expect another call to the call center. Again, that is average. The exponential distribution exhibit Markovian property, as I said. So between customers, they don't affect each other. So they have independent randomness in terms of arriving at the queue. So we call it memorialist. Okay, thing is to understand the queuing systems, right? So we have two elements, right? Queue and service. Queue and service. So we're going to have the number of units waiting in a queue, number of units being served, right? And then waiting time in a queue, service time, and the service at the service facility from the servers. So we have two elements, right, with number of servers to understand the queuing system. So now we're going to use handle notation with parameters, first one, second parameter, and the third one, and maybe you say capacity. So we have three parameters on this textbook. So first parameter is about interarrival time. Interarrival. And the second parameter is about service rate. No. Third is about number of servers. How many servers you're going to have? This interarrival rate follows Poisson distribution or deterministic. So if it follows randomness, it can be Markovian interarrival times or deterministic interarrival times. The second parameter represent service times. So it can follow exponential distribution, which is Markovian service time, or general service times, which is not exponential distribution, or deterministic service times. So number of servers can be 1 server, 2, or S number of servers. The capacity is not here used, but now think of the couple of examples mentioning this. But we can assume we have unlimited capacity or certain value of capacity. So let's say this is capacity. For example, if you see handle notation with MM3, service arrival time of this queuing system follows Markovian distribution, Markovian interarrival times, and Markovian service time with 3 servers. If you see the notation DG4, this system follows deterministic interarrival times, general service times with the 4 servers. Then if you see MG2, this queuing system follows Markovian interarrival time, okay, general service times with the 2 servers. Okay, so, something I need to mention. When you see this queue has several policies. Policy or principles. The customer who arrive, the queue will be solved first. So first in, first out, or first come, first serve. So first customers arrive in the queue will be solved first. And then last in, first out. To arrive the last in the queue, then will be solved first. When do you see these kind of situations? So if you have a book like this, right? And then the come first at time t and time t plus 1, t plus 2. Now you need to pick the book from the shelf, and then which one you're gonna pick the first? From the bottom or from the top? So that maybe from the top, right? So in this case, you see last in, first out. Last in, first out. So that's gonna be last come, first served. Then also you see service in random order called SIRO. They're in order, so you just pick any books, whatever you want. Service in random order, or sometimes round robin. Say right. And then you just use in turns. And you can set up the priority disciplines. For example, if you take airplane, right, without membership, you need to wait in the line, but some airline members will skip the lines, right? They have a priority. So these are the queuing policies or principles. And then next two things we need to talk about key performance indicators. Because this is a system, a service system, or any process, so called a system. Maybe this is a subsystem, which is a system of system. So because we're managing this system, we need to measure performance, right? So without measuring performance, we cannot improve the process. So we need to measure. The system has operating characteristics, so we need to measure performance of the system using key performance indicators. So first one is utilization factor. So it can be expressed as a percentage of time that all servers are busy. So the servers will have a service time, but if you have a limited number of servers, they don't have time to have a break, right? So utilization will be on very close to 100%, right? And even you have cashiers, servers, you may not have customers. So at the call centers, if nobody calls today, no complaints, right? And then no jobs, and you may not have any calls, then the number of units in the queue is 0. So we can see some, so utilization is about business of the server. Then if you have this rotation, probability of having 0 units in the queue. Right? So that means you are not going to have any customers in the system. So probability of having no units in the system. Right. Then if you see notation Tn, there is a probability of n units in the system, not 0. So you may 1, 2, 3, 4. What is the probability of having 1 customers in the queue? What is the probability of having 2 customers in the queue? So what is the probability of having n customers in the queue? And then if you see this notation, PW, it is a probability that arriving unit has to wait for service. What is the probability that you need to wait in the queue when you arrive at the queue? So that is a PW. And we're mentioning W here. W is average time a unit a customer spends in the system, whole system. You need to wait and then receive service and then leave. Right? You arrive in the queue, waiting in the line, and get the service, what you want, and then leave. So total average time a customer spend in the system is W. You may see the different symbols in different textbooks, but we use W in this textbook. These total average time has 2 elements: waiting time in a queue and service time. So the waiting time, average waiting time in the queue for service is WQ. So average time a unit or customer spend in line in a queue for service. There's a WQ, and S actually it's not S in this textbook, but it says The text says average service time is actually average service time is 1 over mu, right? 1 over mu. 1 over mu. I use the symbol as, but as not in the textbook, so it should be 1 over mu, which is average service time. Average service time. And then you may ask, how many customers waiting in the queue? So, for example, you call a doctor's office and they say, how many customers in the queue for now? And can I stop by and come in? And you may ask, right? Instead of using real time, if you know any data regarding the hospital or doctor's office, you may estimate. So what is the average number of units, number of customers, number of patients in line waiting for service? How many customers will be in the line? So let's say this is L, Q. LQ is average number of units in line waiting for service. Then if you see just L, that is average number of units in the system, including waiting, including the number of units in the line and number of units being served. Let's see. Okay, so now we need to consider little slow. I don't know, do we have a slide? No, I don't think so. Yeah. Okay, so little slow. So actually we see, right, number of units, units in the system will be into arrival time. No, not interrupt time. Arrival rate times W. Then LQ will be interval time, no, arrival rate times average time spending in a queue. Then if you see LS, it will be lambda times WS. Okay, so we can use these many different situations. With a different number of, different types of queues. If you assume if we have Markovian interarrival time with Markovian service time with one server, then average waiting time in the system, average time spending in the system will be one of differences between service rate minus arrival rate. So as you have Little's law here, the number of units in a queue for service will be arrival rate times is W. Then you may ask, what is number of units in a queue waiting for service will be W minus WK, W minus 1 of mu. Right? The number of units in a queue, we follow the Little's law, will be lambda times average waiting time in a queue for service. This will be applied to other types of queuing system, but you may have different equations. For example, if you have MMS, multiple servers, right? So then we have additional assumptions. We have a number of S servers, so not single servers, can be 2 or 3. So in that case, arrival follows positive distribution. We assume, because you see the first notation is M, second parameter is also M, right? So service times follows exponential distribution, which is a random variable. And then arrivals wait in a single first in, first out queue policy, and are serviced by the first available servers. So first available servers, first in, first out by any server available. Because we have S number of servers, we have a capacity of the system to serve customers. That is, number of servers S times service rate mu. That's our assumption for this is that number of servers times service rate should be greater than arrival rate. If arrival rate is greater than service capacity, people will come in, but they are not going to leave because the system capacity is already saturated. So, for example, calls arrive randomly at a rate of 5 per hour, So within an hour, you may expect 5 calls and follow a Poisson distribution. The technician service calls at an average rate of 7 per hour. So every hour you expect 7 customers. But the actual time required to handle a call follows exponential distribution. Now you see the arrival rate is random, and the service rate also follows exponential distribution M, and then you have multiple technicians. So you have S number of servers. So you may find many other examples. Okay, so we're going to open Excel later to explain this, but let's have this slide first. So let's assume our arrival, so 2 situations. Arrival rate follows Poisson distribution with arrival rate by 5, and the other system has the same arrival rate, and service rate will be the same. But as a manager, you need to see how many servers you need to have a better customer satisfaction. So in terms of customer satisfaction, customers shouldn't wait for long for next service. So the waiting time should be shorter. So you need to consider how many servers you need to have in addition, right? So you need to calculate utilization with the equations you have. And the key is, you see the WQ, expected time in Q. So when you only have 1 server, so wait expected time in Q is 0.35 hour. So it looks like 20 minutes, right? And if you have 2 servers, so expected average waiting time in the queue is 0.02 hour. That means how many minutes? 2 minutes, 2 minutes, 2 minutes, maybe. No, 3-4 minutes. No, 1.2 minutes. Yeah. And see, probability that a customer waits with the 1 server is 71%. Definitely you need to wait. But if you have 2 servers, customers may not wait, because probability that a customer waits is 0.18. That means 18.8%, very low. So if you are not lucky, you need to wait, but I may expect you are not going to wait in the queue if you arrive at the system which has 2 servers. Okay, so let me open Excel file. So do you have any questions so far?